Hello everyone and welcome back to this course. So last class we discussed about the membrane electrode assembly and its method for the fabrication. It is also requested and suggested for the readers that they should read more literature on fabrication of these assemblies for better understanding. So moving on, we started with the reaction kinetics, and we saw that reaction rates are finite and they are governed by the reaction barriers. And we particularly took the example of rate determining step. Let me write it here. So it is m dot h gives m plus e plus h plus near electrode. So this is the reaction that we were discussing, and we saw that at the triple phase boundary, this is our triple phase boundary, where the catalyst layer is present at the interface of the electrode as well as the electrolyte, and as and when the hydrogen gets chemisorphed and when it comes closer to the metal nanoparticle, we can see that it is very stable with the in the metal interface at the metal with respect to metal interface. And as and when we take this chemisopt hydrogen away from the interface, its free energy increases, which is shown by curve 1. And if we take the example of the product species, that is m plus e plus h plus, as we can primarily concentrate on the proton, which is very stable in the electrolyte domain, and if we take this proton closer to the metal interface, which says 0, that is distance from the interface, we can see that its free energy increases. So if we try to now take the path from reactant to product, that is m dot h to m plus e plus h plus, we can see that there is the path that basically connects the reactant to product species via a common point called as activated state A, and this is the state which every reactant species or any product species has to pass through in order to get converted into the respective species. So if I take the example of forward reaction, wherein m dot h gets converted to m plus e plus h plus, this chemisopt hydrogen species has to go through this activated state. In other words, it has to overcome this reaction barrier delta G1 if it wants to get converted into m plus e plus h plus. Same is the case with the reverse reaction. If we take the example of m plus e plus h plus, it also has to cross through this activated state in order to get converted into soft hydrogen, that is m dot h, and for that it has to overcome the reaction barrier, that is delta G2. So that is how we can find a common path, and we can find out the activated state. That is all has been explained here. Let us move on and we see that how we can find out this activated state. So that is governed by probability. So let me write about the activation energy. So this is activation energy. For that we have to first, let us define this activated state. So A is your activated state, of the species. So species of our interest, it can be chemisopt hydrogen or the proton, depending on which reaction we are interested in. So we have to understand that only activated species can determine the rate of reaction. In other words, not all species get converted into activated ones. Only those who are in activated state can undergo the reaction, and then those species can only determine the rate of reaction. So the probability of this finding activated state A is basically exponentially dependent on the size of your activation barrier. So, till now we mentioned that this barrier is nothing but the reaction barrier. Now, let us make it more specific and call it as an activation barrier, because overcoming that barrier we can activate the reaction. So, that is why that barrier is called as activation barrier. And what is this probability? Probability of activation depends or is dependent on this activation barrier, and this is the expression. So, there this P stands for, this is the probability so probability of converting these species into the activated ones. Delta G, let me write it here, delta G is your energy barrier between reactant and the activated state. So, we should understand that it is a barrier between the reactant and the activated state, not the reactant and the products. R and T are basically universal gas constants. Constant and the operating temperature. Let us talk more about it. So, let me take the example of forward reaction. So, let us write about the reaction rate in forward reaction, wherein your R goes to P. So, that is given by V1. Okay, V1 stands CR F1 e to the power minus delta G by RT. So, this is star. V1 is basically, let me write it like this. So, this is your reaction rate to products basically. See, R star is basically reactant surface concentration and this is in mole per centimeter square, in other words moles per unit area, and F1 is basically your decay rate to products. So, what is this surface reaction or surface concentration? So, let me highlight that. So, let us take the example of only one electrode, hydrogen in this case. So, at this, let us say when we are supplying this hydrogen through bipolar plate. So, we have bipolar plate. So, this is your hydrogen and hydrogen. So, when it is supplied with some concentration, so this is what it forms as a bulk concentration, because it is away from the catalyst sites. These are the catalyst sites here. So, when we are drawing some current, we have to understand that the concentration what is supplied at the bulk is different from what is available at the reaction site. So, reaction site which determine the actual concentration, they are called as surface concentration. So, we can expect concentration here as to be Cr star, and here this is called as surface concentration. And what is being supplied is our bulk concentration C0R. So, this is the bulk concentration. So, that is a difference. So, when we are drawing no current, we can say that the bulk concentration is same as that of the surface concentration. However, as when we start drawing the current, in case of fuel cells, or when we supply the current in case of electrolyzers, the surface and bulk concentrations vary, they differ from the reference values. Let us move on. Let me write little more about the decay rate. So, decay rate is basically, decay rate is equal to probability of reactants getting converted into products divided by tau A. So, let me write this. This is the probability of reactant getting converted into product, and what is tau A? Tau A is the lifetime of the activated state. So, when I say, for example, when this probability of reactant getting converted into product is, let us say, half, what does it imply? It implies that the activated species can fall either way. In other words, there can be recombinations possible. And let me also write for tau A, that is lifetime. It is given by, let me write this, lifetime of activated state, which is equal to h by 2 k T. So, h is your Planck's constant, and k is the Boltzmann constant, small, and T is the operating temperature, right. So, let us talk about the net rate of reaction. So, we need to understand that. So, we are talking about only one electrode at this point. So, if I take the example of hydrogen electrode, at the catalyst we have two reactions possible. One is a forward reaction, the other one is reverse reaction. So, forward reactions means we can consider that H2 giving 2H plus 2 electrons. This is our forward reaction. What is the reverse reaction possible? That is the combination of protons and electrons to form the product hydrogen. So, we are trying to basically consider only one electrode, and we will find out the forward rate of reaction, reverse rate of reaction, and once we subtract one from the other, we will be able to find out the net rate of reaction. So, that is what I will going to write here. So, H2 giving 2H plus 2 moles of electrons. This is our forward reaction. Reverse reaction is the combination of protons and electrons forming water, forming gaseous hydrogen. And this has got reaction rate as V1, this has got reaction rate V2. So, what is our net rate of reaction? Net rate of reaction, it is V, which is V1 minus V2. So, we can also write V2 minus V1, does not make any difference as such. So, let us substitute, this is Cr star F1 e to the power minus delta G1 by RT. Please remember this, the entire term is superscript, minus Cp star F2 e to the power minus delta G2 by RT. So, if you recall our previous diagram wherein we had related delta G1 and delta G2, so we can write that here. So, we know that is delta G reaction as delta G1 minus delta G2. I can draw that diagram one more time here. So, it is like this. So, this is our delta G1, this is delta G2, and this is our delta G reaction. The same figure has been drawn one more time. So, this is our activity state A. So, delta G reaction is basically delta G1 minus delta G2. I can write the other way around as well, delta G2 minus delta G1. However, we are trying to favor the forward reaction. So, we are trying to write everything in delta G1 form. So, this is the delta reaction barrier for the entire reaction. So, let us go ahead and write this. Rate of reaction is basically rate of change of concentration per unit time. So, it is equal to Cr star F1 e to the power minus delta G1 by RT minus Cp star F2 e to the power minus delta G2 by RT. Let us substitute for delta G2. So, it is equal to Cr star F1 e to the power minus delta G1 by RT minus Cp star F2 e to the power. Let us substitute for delta G2, it is delta G1 minus delta G reaction by RT. So, if we see this, our reaction rate is inversely proportional to the activation barrier. So, it is typically delta G by RT. So, in other words, what I can say is, if our activation barrier is small, the reaction rate will be fast, or particular rate of reaction will be fast. So, the activation barrier for the, if I consider the forward reaction is smaller compared to the reverse reaction, the forward reaction will be favored, and then that is how we can say that the net current will be in the forward direction. If we want the reverse reaction to be favored, we need to tune the activation barrier for this delta G2 for this reaction such a way that delta G2 is smaller than the delta G1, and then in that case only the reverse reaction will be favored. So, let us talk about the exchange current. Exchange current density. We know V is our reaction rate, which is basically change of concentration or moles per unit time. So, this is in mole per second, right. And what is our current? Our current density, J is, let us say, current density. So, this is basically Nf times V, right. So, let us write for the forward reaction. So, forward current density so let us write it as J1, this is Nf. So, we need to substitute for V1 here. So, it is Cr star F1 e to the power minus delta G1 by RT, and similarly reverse current density it is J2 Nf. So, we need to write it for the V2, which is Cp star F2 e to the power, again in the delta G1 form. So, it is delta G1 minus delta G reaction by RT, is all in superscript. So, let me go ahead So what we are trying to do here is, so we have taken one electrode, and on that electrode we have considered two reactions happening. One is in the forward direction, the other one is in reverse direction. So we have found out the reaction rate for the forward reaction. We have also found out the reaction rate for the reverse reaction, and we assume that since the forward reaction is also happening and the reverse reaction is also happening, there should be forward current density and the reverse current density as well. So at equilibrium, I can say equilibrium, both forward and reverse current densities balance, basically both are same, so they balance each other. So that the net current or current density, net current density is 0. Okay. So how do we do that? So we basically say J1 is equal to J2, that equals one more parameter we are going to introduce, that is called as J0, and J0 is basically exchange current density. So this is, please remember, this is at the equilibrium. In other words, when if you are drawing no current from the fuel cell, we can write for the exchange current density. If you are drawing some current, then J1 is not equal to J0. There will be some differences, and we cannot write J1 is equal to J2 as J0. So how we can express this graphically? Let me use a separate page. So this is at equilibrium. This is at equilibrium, wherein the forward and the reverse reactions, they have the equal rates, which plus electrons. So, and this is our activated state. This is the delta G1, and this one is our delta G2. This is again our free energy. Both are same at the equilibrium. How it changes if there is some reaction that is favored. Let's assume forward reaction will be favored. So in that case, our delta G1 has to be lesser than delta G2. So the image will look like this. So this is still the H2. So I can write here it is H plus electrons, and this one this is our delta G1. This will be delta G2. So as we can see here, this delta G1 is less than delta G2. Therefore, forward reaction will be favored. And what will be the case if you want to reverse the reaction? We draw it here a little bigger. So it will be something like this. As you can see, this is our delta G1 and this is our delta G2, activated state. This is again free energy, H2, H plus electrons, So, in this case the reverse reaction will be favored because the delta G1 is far greater than delta G2, or in other words delta G2 is smaller than delta G1. So, the reaction barrier for the reverse reaction is smaller, and therefore, reverse reaction will be favored. Or in other words, if you want to go for the electrolysis wherein the reduction of hydrogen is to be taken place, we have to ensure that the reaction barrier for reverse reaction, that is combination of protons and electrons, should be smaller than that of the oxidation reaction, and that is how we can go ahead with the electrolysis process. So, that is all about the reaction barriers, how we can tune about it. Now, let us try to make it slightly technical and see that how we can go ahead and find out this reaction barriers and how we can relate them with the potential that we are operating the cell at. So, we will go ahead with the Butler-Volmer equation in the upcoming class and stop here. Thank you for that.